All right, this is going to be our biggest topic for this chapter. So we'll be talking about how to determine how much electricity the cell will produce if we have a spontaneous reaction, or how much electricity is required to force the chemical reaction to occur if we have a non-spontaneous reaction. So first thing, the reason why the electrons flow from the anode to the cathode is because the cathode has a lower electric potential energy than the anode does. You might know from physics that 1 volt equals 1 joule per coulomb. So if you've done physics, you have talked about coulombs. So the potential difference is the difference in electric potential between the two metals, and it's going to be measured in volts. So if we think about volts, that is what our electricity is going to be measured in, and voltaic cells are spontaneous, so voltaic cells produce volts of electricity spontaneously. All right, in Regents chemistry, we had table J, which I personally hate. So table J was our activity series, and that listed the more reactive metals up on top and the less reactive, like gold, silver, copper, down at the bottom. The reason why I hate table J is because table J comes from this table. This table is super helpful. And table J feels a little random, I feel like. All right, so what we have here is we have a whole bunch of different reduction, half reactions, and their corresponding voltage. Basically, what we're going to do is we're going to write out our two half reactions, and then we are going to use this table to see what their voltage would be, and then that will give us the voltage of the cell. Very simple. If we get a positive value, that tells us that the cell is going to produce volts spontaneously. If we add up the two half reactions, get a negative value, that tells us that that is not a spontaneous reaction, that it would require that much electricity in order to force the reaction to occur. All right, so hydrogen is the standard. So that's on here as a 0 value. And then things that are easier to reduce than hydrogen have positive values, and harder would be negative values. This is another voltage table. This is the one that is in your note packet. This also is in your textbook. We will need to reference this while we're doing our homework questions. All right, so the voltage is always written for a reduction half reaction. So if we need an oxidation half reaction, it's going to be the reverse. So then you just reverse the sign. Pretty intuitive. I think that makes sense, but I'm going to repeat that once more. These are all reductions. So if we need an oxidation, that's the reverse. So therefore you would reverse the sign. All right, the more positive the reduction potential, the more likely it is that that substance is reduced. So then we could do the opposite of that. The more negative the reduction potential, the less likely it is to get reduced, and the more likely it would be to get oxidized. This last one here is important. If we change the stoichiometry, that will not change the value of the reduction potential. So if you are, have twice as many of the voltage. But if we flip-flop it, it will change the value of the voltage. It will flip the sign. And we're going to do a bunch of examples now. Before we get to our examples, just a note on notation. So E is going to be the voltage, And then sometimes you'll see cell written there. That would be the overall reaction for the voltaic cell, or the overall voltage for the voltaic cell. If it's positive, then we have a spontaneous reaction. So that's very important to know. If we see this little symbol here, that just means that we're under standard conditions, which standard conditions is 1 molar solutions at 25 degrees Celsius, which is just a touch warmer than room temperature. Or if we had gases, it would be 1 atm of pressure. All right, so now we will do our first example. So we have very basic reaction: zinc metal plus the copper ion makes zinc ion and copper metal. So first thing we would need to do is to write out our half reaction. So one of our half reactions would be zinc 0 goes to the zinc ions by losing 2 electrons. That would be an oxidation. And then my other half reaction would be the copper ion gains 2 electrons to get reduced to make copper 0. Now what I do is I go to that table and I find those 2 half reactions. So it just takes me a little while to scan the table to find those 2 half reactions. All right, the zinc one is about 2/3 of the way down on the table, but that's for the zinc ion getting reduced. So we have to flip-flop the sign. So it would be positive 0.76 volts. So again, on the table, it's written for the reduction, which would be the reverse reaction, and it's negative. We want the oxidation, so we flip the sign. All right, then we find our copper half reaction, and that is about halfway down the table, and that is positive 0.34 volts. Now, it was already written as the reduction, so we do not change the sign because we wanted what was already on the table. In order to figure out the voltage for the cell, we just add those 2 things up and we get 1.10 volts. Because this is a positive value, we would know that the reaction should occur spontaneously, and so this would be set up as a voltaic cell. All right, so if they give you the reaction, very straightforward. You write out your 2 half reactions, you use the table, and get the overall voltage. Sometimes they will give you a problem without giving you the full reaction. They would just give you the materials. So they would say, you've got zinc metal, aluminum metal, zinc nitrate, and aluminum nitrate. Figure out what the voltage should be. When you do that, what you do is you look at Table E, or Appendix E in the back of your book, or the table that's in your note packet, and you find your 2 half reactions. We obviously need 1 reduction and 1 oxidation, so you're going to have to flip one of the 2 half reactions. So you just flip whichever one is going to make you come out to a positive voltage, or the larger voltage. So we'll take a look at an example like that. All right, now this is the same example that we did a few minutes ago, but we're going to pretend like we don't know which one's going to be oxidized and which one's going to be reduced. So they just told us that we had zinc, we had copper. It's a galvanic cell. That means voltaic cell, so therefore it's spontaneous. So we know we're going to have a positive overall voltage. So determine the voltage, the anode, and the cathode. So we would look up our 2 half reactions, which I already have written here. So these would be off of the table. Now again, they come off of the table as reduction. Should you flip in order to end up with a positive overall voltage, or the most positive if they were, 2 ways to do that. All right, so we think about it. If I want my overall voltage to be positive, I would need to flip the zinc one. Because if I flipped the copper, then I'm going to end up with a negative voltage overall. So if I flip the zinc one, making zinc get oxidized, then the voltage for that would be plus 0.76. And then the copper ion would still get reduced. Again, you need one reduction, one oxidation. So that's going to be 0.34. And overall, that would give me 1.1. So that would be my overall voltage. The anode is where oxidation occurs. So the anode is going to be zinc, and the cathode would be the copper metal. All right, we have another example here. So it says, what is the standard EMF? That just means what is the voltage of an electrochemical cell made of a CD electrode in a 1 molar CD solution and chromium with a chromium solution. And they already gave me the reduction potentials, which this is not in your reference table. The reduction potentials are not in your reference table. So if you had an exam question where you needed the values, they would have to be given like they are here. Okay, so we think about which way or which one we're going to have to switch, because we're going to need one reduction, one oxidation. So if we switch the chromium one, that would allow us to get a positive voltage. So Cr is going to get oxidized to make Cr plus 3 and 3 electrons. And the voltage for that is going to be positive 0.74 since I flipped it. CD is going to stay getting reduced. That's going to stay as negative 0.40. So my overall voltage would be 0.34. So it's still going to be spontaneous. All right, now if we needed to do the overall reaction, so sometimes they might ask us for the net reaction. Remember, electrons need to be equal and opposite, meaning if I'm losing 3 electrons, I must also be gaining 3 electrons, and that's not the case here. So we would need to multiply the Cr1 by 2, because that would give us 6 electrons, and the CD reaction by 3, because that would give us 6 electrons. So my overall reaction, had they asked me for that, would be 2Cr plus 3 of the cadmium ions, produce 2 of the chromium ions, and 3 of the CD metals. So that would be my overall reaction had they asked me for that. Remember, changing the coefficients does not change the voltage, so that's going to stay at 0.34. And this is just that same reaction that we were doing. So we already figured out the overall voltage on the previous slide. And we figured out that the Cr metal was getting oxidized because that was the one that we flipped. So Cr was the anode and cathode would be the CD because that would be the metal associated with the reduction.